Hello physics students. In this video, we're going to do a practice calculation with the law of conservation of momentum. But I want to remind you again that there are two ideas in this unit, two main ideas. The first one is impulse, which is defined as force times time equals the change in momentum of an object or a system. The second main idea is that if a system is isolated, in other words, it doesn't receive an impulse, then Pi equals Pf. So this calculation will be practicing Pi equals Pf. So the situation is like this. We've got two objects, one more massive than the other. The red car has the mass on it again. And then the blue car sitting here at rest together. So what is the momentum of the system? Zero, right? Nothing is moving. And then what I'm going to do is I'm not going to supply an impulse to it from the outside world. All that I'm going to do is tap this release pin, which won't really influence the system much. It's not like I'm going to be nudging it forward or backward. I'm just going to tap down and the spring will pop out. And then we're going to see what happens as a result of the spring popping out. This is like a model of basically a little small explosion. The spring being like the explosive. So Pi equals 0, right? I tap this, which will not add momentum. I'm just going to release the spring. So Pi equals 0. And when these things shot apart, what was Pf? And a lot of people say, wow, I don't know. I saw something shoot this way, something shoot that way. You should know. I told you what Pi is, right? Pi was 0. What is Pf? 0, right? And then some people might be saying, but how could Pf be 0 if things are shooting apart? There's now mass and velocity, so now there's momentum. Maybe Pi does not equal Pf. It does, because remember, everything in this topic, forces, momentums, impulses, are all vectors. So if this shoots out with 10 units of momentum, the momentum of this must be negative 10. 10 and negative 10, 0. Pi equals 0, Pf equals 0. This also explains why the more massive object has to go back slower. Now before, we used Newton's laws for this. We said that equal force is more mass, less acceleration. Equal force is less mass, more acceleration. So we use Newton's laws, and that's perfectly fine. Again, everything in this topic is redundant. But this time, using momentum to explain why this went away faster than this, if the mv of this has to equal the mv of that, with more mass, you need less velocity, so that mv balances to mv over here. So there is the concept. Those are the concepts of this kind of collision. But what we're going to do is do a calculation practice of this. Okay? So see how we could, maybe knowing one velocity, calculate the other. But I was thinking about this, and also thinking about a little while ago in class, some of the students in class were saying how much they enjoyed the time traveling in the class, and I haven't done that in a while. So I thought maybe it'd be fun to do a little time traveling again and incorporate something we did in the past into this video. And the thing that we did in the past, everyone loved this, was when I shot off the tennis ball cannon. It's basically almost the same situation. Instead of these two cars, I have the tennis ball cannon and the tennis ball shooting out, and not a spring, but the hairspray exploding these apart. But there's a bit of a problem. I realized that when I recorded the video, and I did that lesson, that video lesson, I didn't have any way to measure the distance. I didn't think I needed to, so I just shot the cannon off, and there's nothing in the view to measure distance so we could do some calculations of velocity. So knowing that, what I first have to do is I have to leave you for a little bit. I'm going to use the time machine on myself, and I'm going to go back in time to when I did that and sneak a meter stick into the view. I'm going to put it on the table so that when I send you back in time, we'll have a visual reference for the distance of, that the tennis ball cannon rolls. So I'll be back in a minute. Okay, so I'm back. I hope I wasn't gone too long. Now, before I send you back to that day, I just want to tell you about something kind of interesting I was thinking about during my journey. Suppose you had a photographic memory and you didn't need to go back in time. You remembered exactly what I did over a month ago with that tennis ball cannon. Up to 1 minute ago, about a minute ago, before I went back in time, you would have remembered that on that table there was no meter stick. But now, after I went back in time, you would swear, if you had a photographic memory, that that meter stick was there the entire time. Because what I did is I went back before you recorded that memory of the table having no meter stick on it. And then I put the meter stick there, and then over a month ago, now you recorded that memory of a meter stick being there. So now, at this moment, the meter stick has always been there in your photographic memory since about a minute ago. Mind-blowing stuff, time travel. You could check YouTube, you could check Edpuzzle, and that meter stick is there. I altered not only YouTube, Edpuzzle, I altered even your memory just by that little bit of time travel. Crazy stuff, crazy stuff. So, but you probably don't have a photographic memory. So I'm going to now send you back in time to that moment. And what you're going to do is watch the tennis ball cannon carefully. And we're going to analyze it in terms of momentum. I'm going to be watching too, and I'm going to use my stopwatch here to time how long it took that tennis ball cannon to roll back and hit the books. You could do it yourself if you want, or you could just let me do it. And now we have that meter stick right there to estimate that the distance it rolled back was approximately 1 meter. From that 1 meter distance and the time I'm about to record, we'll get the velocity of the tennis ball cannon. Then we're going to use momentum to analyze the velocity of the tennis ball. So here we go. Brace yourself. All right, so if this shoots out, remember the point of this is to analyze this in terms of Newton's third law. So let's go, let's see what happens. Not bad, okay? Not bad at all. Okay, so hope that wasn't too jarring. I've got a time for the amount of time it took the tennis ball cannon to roll back and hit those books. I don't know if you timed it, but here's the time I got, 0.83 seconds. So let's see if we could analyze and figure out from this new idea, momentum conservation, how fast the tennis ball shot out. So the first thing, so tennis ball cannon, and from that, I could figure out its backward speed, or its velocity, from v equals distance over time. So 1 meter over 0.83 seconds. Let's get a calculator. 1 divided by 0.83, 1.20 meters per second. So all right. Now, as we saw in the video, it rolled back, ball went forward. to use momentum to figure out the velocity of the tennis ball, we need masses. So, got an electronic balance here. Tennis ball cannon and tennis ball, here they are. I didn't bring these from back in time. I had them in the present moment in the storeroom, so I got them out. Okay, 1.31 kilograms. So M of cannon, 1.31 kgs. And the tennis ball, 56 grams, 0.056 kilograms. Hopefully the track's not in the way. Okay, so let's now use momentum conservation to figure out the speed of that ball. Remember I said in the previous video, I strongly recommend drawing a diagram with every momentum conservation calculation. So here is the situation, before and after. So you don't need a fancy diagram. I don't need to draw the cannon. I could just do, again, boxes. It's just a schematic diagram of what's happening. 0 and 0.056 kgs, 0. After the hairspray ignited, (1.20 meters per second). Tennis ball. Right? Much longer arrow, really, if I wanted to draw it accurately to scale. We don't know what this is. We're trying to find it. Now, I left something off on purpose. Do you know what it is? Hopefully you said minus sign, right? If this is going backwards, I'm going to put a minus sign so the forward motion comes out positive. So once again, we always start with the formula PI equals PF. What's PI? 0. Nothing's moving. You don't even need to show that calculation. You could just write 0. What about the momentum of the system after? What is it? 0 again, right? 1.31 kgs, negative 1.2, plus should have started a little bit more to the left. So now I just need to solve for V final of the tennis ball. So I will take these and multiply them together. And I get 1.572. So this is negative 1.572 plus 0. Okay. I'll add the 1.572 to the other side. Divide by 0.056. And I get V final 28.1 meters per second. Now, may not sound dramatic, but that's because it's meters per second. If I want to convert to miles per hour, you basically multiply by 2.25. That's the conversion, and it's 63 miles an hour. So, you know, maybe not that impressive, but still pretty impressive. Over 60 miles an hour, the tennis ball got shot out of the cannon. All right, so let me create a pause. If you haven't already copied all this down, I'll give you a chance to catch up. All right, so let me just ask you a question now. Looking at these calculations, can you tell me the momentum of the tennis ball without doing any calculations? Just looking at the numbers there, don't punch anything on your calculator. All right? Maybe I'll create a pause, give you a chance to look that over and see if you could determine from those numbers without calculating the momentum of the tennis ball. All right, hopefully you saw that it must be positive 1.572. And I'll leave the units off because I'm just like, we're looking at the concepts. How do I know that? Momentum of the system was 0 before. What was it after? 0 after, Pi equals Pf. If the cannon had a negative 1.572, backwards, the only way for momentum to be conserved is for the ball to have positive 1.572, so they add to 0 after, just like before. Okay, so a little concept there. All right, so once again, we did a little practice with Pi equals Pf. Momentum of an isolated system remains constant. You can't have anything affecting the system from the outside. Today, we looked at 0 momentum, 0 momentum, and the setup was basically like this. So I hope you enjoyed the video. I hope you enjoyed the time travel. I'm sorry if I invaded into your mind and altered your memories by going back before you actually recorded your memories. If that's going to create a problem, I apologize. I don't think it should. I think everything should go smoothly forward in the forward direction of time from here on out. All right, so I'll see you in the next physics video.